Tonight, we are going to talk about a faint smudge of light in the autumn sky that most people have never once noticed. You can see it with your naked eye if you know where to look, barely visible, easily mistaken for a wisp of cloud. What you are actually looking at is 1 trillion stars, a galaxy called Andromeda, located 2.5 million light-years from your eyes, and moving toward us right now at 245,000 miles per hour. By the end of tonight, you are going to understand the full scale of what that means, how our Milky Way measures against Andromeda, and why, despite being able to see it on any clear night, it represents a distance our universe will simply never allow us to cross. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what Andromeda represents, we need to establish where we are. Let's start with Earth, a rocky world 8,000 miles in diameter, not particularly large as planets go. Jupiter, the giant of our solar system, could swallow over 1,000 Earths. But Earth is special for a different reason. It sits 93 million miles from the Sun, close enough that water stays liquid, far enough that it doesn't boil away. This narrow band of space around any star is called the habitable zone. Too close, and you get Venus, a hellish greenhouse where lead melts on the surface. Too far, and you get Mars, a frozen desert where water exists only as ice. Earth sits in the middle, in the Goldilocks zone where conditions are just right. The Sun itself dominates everything around it. 865,000 miles across. It's so large that 1 million Earths could fit inside its volume. It contains 99.86% of all the mass in our solar system. When you add up all 8 planets, all their moons, every asteroid in the asteroid belt, every comet, every grain of dust, all of it together makes up less than 0.14%. The Sun is everything. Light takes 8 minutes and 20 seconds to travel from the Sun to Earth. This means, when you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun vanished right now, we wouldn't know for 8 minutes and 20 seconds. Earth would continue orbiting empty space, still bathed in the last light that left before the Sun disappeared. The solar system is vast by human standards. Neptune, the outermost planet, orbits at about 2.8 billion miles from the Sun. Light from the Sun takes over 4 hours to reach Neptune. But even Neptune isn't the true edge. Beyond the planets lies the Kuiper Belt, a region of icy bodies where Pluto orbits among thousands of similar frozen worlds. These are remnants from the solar system's formation, chunks of ice and rock that never coalesced into planets. And beyond the Kuiper Belt, much farther out, lies the Oort cloud. This is a vast, spherical shell of comets surrounding our entire solar system like a bubble. It begins about 186 billion miles from the Sun. It extends outward to nearly 2 light-years. That's 12 trillion miles. The Oort cloud represents the absolute edge of the Sun's gravitational influence. Beyond it, you're in interstellar space, the void between stars. And that void is enormous. The nearest star to our Sun is Proxima Centauri, a small red dwarf, much dimmer and cooler than our Sun. It sits 4.24 light-years away, 25 trillion miles. If you could drive there at highway speed, the trip would take about 43 million years. Even light, traveling at the fastest speed possible in the universe, takes over 4 years to cross the gap, and Proxima Centauri is close. Unusually close, actually. It's our nearest neighbor. Most stars are much farther away. Sirius, the brightest star in our night sky, sits 8.6 light-years away. Vega, a brilliant blue-white star, sits 25 light-years distant. Betelgeuse, the red supergiant marking Orion's shoulder, sits about 550 light-years away. The space between stars is almost unimaginably empty. Now, zoom out. Imagine you could see all of these stars at once. Our Sun, Proxima Centauri, Sirius, Vega, Betelgeuse, every star visible in Earth's night sky. Every star ever catalogued by astronomers. All of them, hundreds of billions of them, belong to one structure, our galaxy, the Milky Way. If you could view the Milky Way from outside, from a position far above its disk, you'd see a magnificent spiral. A bright central bulge, surrounded by sweeping spiral arms, all rotating slowly around the center. The entire structure spans about 100,000 light-years from edge to edge, 600 quadrillion miles. It contains somewhere between 100 billion and 400 billion stars. The uncertainty comes from the fact that we're inside it, trying to count stars while embedded within the structure itself. It's like trying to count all the trees in a forest while standing in the middle of it. Some stars are hidden behind dust clouds. Some are too faint to detect. Some are in regions we simply can't observe from our position. But the number is certainly in the hundreds of billions. Each one a sun, potentially with its own planets. Among those hundreds of billions of stars, our sun is fairly ordinary. A middle-aged yellow dwarf, neither particularly large nor particularly small. We sit about 26,000 light-years from the galactic center. Not in the core, where stars are densely packed. Not on the outer edge, where stars thin out. But somewhere in between, in a relatively calm region between spiral arms. This region is called the Orion Spur, and it's been a safe, stable neighborhood for our solar system for the past 4.6 billion years. The Sun orbits the galactic center at about 500,000 miles per hour. That sounds incredibly fast, and it is by any human standard. But at galactic scales, it's quite slow. It takes about 225 million years for the Sun to complete one orbit. Think about that. Since Earth formed 4.6 billion years ago, we've completed only about 20 orbits around the galaxy. Dinosaurs appeared less than one galactic orbit ago. All of human history, from the first hominids to today, has occurred in less than 0.1% of a galactic year. At the center of the Milky Way, buried beneath layers of stars and gas and dust, sits a supermassive black hole. We call it Sagittarius A. It weighs about 4 million times the mass of our Sun. All of that mass compressed into a region with a radius smaller than Mercury's orbit around the Sun. The black hole doesn't emit light, by definition. Nothing escapes from inside a black hole, not even light. But we know it's there because we can watch stars near the galactic center whipping around it at incredible speeds. Some of these stars complete an orbit in just 16 years, accelerating to nearly 2% the speed of light at their closest approach. By tracking these stellar orbits, astronomers have proven that there's something massive and invisible at the exact center of our galaxy. The only explanation is a supermassive black hole. This discovery earned the Nobel Prize in Physics in 2020. The Milky Way is home. Everything humanity has ever known exists within this galaxy. Every person who has ever lived, every civilization that has risen and fallen, every moment of history. All of it happened here. For most of human existence, we didn't know any of this. We saw a band of light stretching across the night sky and knew it was something significant, but we had no idea what. Ancient Greeks called it galaxias kyklos, the Milky Circle. Some cultures thought it was a river of milk spilled by the gods. Others thought it was a road traveled by souls. Even as late as the early 1900s, most astronomers believed the Milky Way was the entire universe. Everything that existed was contained within it. Then, in 1923, everything changed. An astronomer named Edwin Hubble was working at Mount Wilson Observatory in California. He had access to the 100-inch Hooker telescope, the largest and most powerful telescope in the world at that time. Night after night, Hubble pointed this instrument at a fuzzy patch of light called Andromeda. He wasn't the first person to notice it. Persian astronomer Abd al-Rahman al-Sufi had observed it in 964, describing it in his Book of Fixed Stars as a small cloud. European astronomers had catalogued it centuries later. Simon Marius, a German astronomer, observed it through an early telescope in 1612 and described it as looking like a candle flame seen through horn. Charles Messier, a French comet hunter in the 1700s, listed it as number 31 in his catalogue of things that aren't comets. He was frustrated by fuzzy objects that looked like comets but didn't move like comets, so he catalogued them so other astronomers could ignore them. The Andromeda object became Messier 31, but for all this observation, no one knew what it actually was. The debate that consumed astronomy in the early 1900s was simple. Were these spiral nebulas, as they were called, clouds of gas within our galaxy? Or were they something else entirely? Some astronomers argued they must be relatively nearby, part of the Milky Way, perhaps regions where new solar systems were forming. Others, including philosopher Immanuel Kant, nearly 2 centuries earlier, speculated they might be island universes, separate galaxies far beyond our own. But speculation wasn't enough. Astronomy needed measurement. Hubble provided that measurement. He took long photographic exposures of Andromeda, letting light accumulate on the photographic plates for hours. When he examined these plates, he could see individual stars within the nebula. And among those stars, he found something crucial: variable stars. Stars that changed in brightness over time, pulsing with a regular period. He identified them as Cepheid variables, a type of star that had been extensively studied by Henrietta Swan Leavitt a few years earlier. Leavitt had discovered something remarkable about Cepheids. There's a direct relationship between how fast a Cepheid pulses and how bright it actually is. A Cepheid that pulses slowly is intrinsically much brighter than one that pulses quickly. This relationship is incredibly useful for measuring distances. If you measure how fast a Cepheid pulses, you know its true brightness. If you know its true brightness and you measure how bright it appears from Earth, you can calculate how far away it is. It's the same principle that lets you judge the distance to a car at night by how bright its headlights appear. A car 100 feet away has bright headlights. A car a mile away has dim headlights. If you know how bright the headlights actually are, you can calculate the distance by measuring how bright they appear. Hubble found Cepheid variables in Andromeda. He measured their pulsation periods carefully over many nights. He used Leavitt's relationship to calculate their true brightness. Then he compared that to their apparent brightness as seen from Earth. The calculation was straightforward. The answer was shocking. 900,000 light-years. This was later refined as better calibrations of the Cepheid relationship became available. Modern measurements put Andromeda at about 2.5 million light-years. Hubble's initial estimate was off by a factor of about 3, but the conclusion was still revolutionary. Andromeda wasn't a cloud of gas within the Milky Way. It wasn't part of our galaxy at all. It was an entire separate galaxy. A collection of billions of stars, far beyond our own, sitting in the vast darkness of what we now call intergalactic space. Hubble announced his findings in 1924 at a meeting of the American Astronomical Society. The response was immediate and profound. If Andromeda was a separate galaxy, then what about all the other spiral nebulas scattered across the sky? Were they all separate galaxies too? The answer was yes. The universe, overnight, became almost incomprehensibly larger. The Milky Way wasn't the universe. It was just one galaxy among many, perhaps among countless galaxies scattered through infinite space. This discovery is considered one of the most important in the history of astronomy. It expanded humanity's cosmic horizon from one galaxy to a universe of galaxies. And Andromeda, that faint smudge, barely visible to the naked eye, became the first galaxy proven to lie beyond our own. The first step into a much larger cosmos. So what is Andromeda? It's a spiral galaxy, like the Milky Way, but it's larger, significantly larger. Where the Milky Way spans 100,000 light-years from edge to edge, Andromeda stretches to about 220,000 light-years in diameter, more than twice as wide. The Milky Way contains between 100 billion and 400 billion stars. Andromeda contains roughly 1 trillion stars, at least twice as many as our galaxy, possibly 3 times as many. That's 1 trillion suns, each one potentially with its own system of planets. If you started counting them one per second, it would take over 31,000 years to count them all. The Milky Way has a total mass, including dark matter, of about 1.5 trillion times the mass of our Sun. Andromeda weighs in at roughly 2.5 trillion solar masses, about 65% more massive than our galaxy. This makes Andromeda the dominant galaxy in our local group. The local group is the name astronomers give to our small cluster of galaxies. It includes the Milky Way, Andromeda, the Triangulum galaxy, a smaller spiral, about 60,000 light-years across, and about 80 smaller dwarf galaxies, orbiting the larger ones, like moons around planets. All of these galaxies are bound together by gravity. They orbit around their common center of mass, held together despite the expansion of the universe pulling everything else apart. And Andromeda sits at the top of this hierarchy, the most massive galaxy in the group, the gravitational anchor around which everything else orbits. Like the Milky Way, Andromeda is a spiral galaxy. It has a bright central bulge packed with older, yellow, and red stars that have been burning for billions of years. Extending from this bulge are spiral arms, sweeping patterns traced out by regions of active star formation. These arms glow blue in photographs because they're filled with young, hot, massive stars. Stars that burn so brightly they live only a few million years before exploding. Between the arms, you find older, redder stars that have been burning steadily for billions of years. The spiral structure exists because of the galaxy's rotation. As the galaxy spins, density waves move through the disk like ripples on a pond. Stars and gas pile up in these density waves temporarily, then move through and disperse. It's like a traffic jam on a highway. The jam stays in one place, even though individual cars move through it. Spiral arms work the same way. At the center of Andromeda, like at the center of the Milky Way, sits a supermassive black hole, but Andromeda's black hole is much larger than ours. Where Sagittarius A star weighs about 4 million solar masses, Andromeda's central black hole tips the scales at roughly 100 million times the mass of our Sun, 25 times more massive. This enormous black hole dominates the core of the galaxy. Stars, within a few light years of it, orbit at thousands of miles per second. Gas clouds occasionally fall inward, spiraling down toward the black hole. As they fall, friction heats them to millions of degrees. They emit X-rays and ultraviolet light before finally crossing the event horizon and disappearing forever. The black hole's gravity also regulates how stars form throughout the galaxy. When too much gas accumulates near the center, it falls toward the black hole, heats up, and radiates enormous amounts of energy. This radiation pushes back on surrounding gas, preventing it from collapsing into stars. It's a feedback mechanism that keeps the galaxy from using up all its gas too quickly. Andromeda's core has something else unusual: a double nucleus. When astronomers look at the center with powerful telescopes, they see two bright concentrations of stars instead of one. For years, this was puzzling. Why would the galactic center be split into two distinct regions? Eventually, detailed observations revealed the answer. Andromeda's supermassive black hole isn't at the geometric center of the galaxy. It's offset by about 5 light-years. The brightest concentration of stars surrounds the black hole, orbiting it tightly. The second concentration sits at the actual geometric center of the galaxy, which no longer contains the black hole. This displacement almost certainly happened because Andromeda merged with another galaxy in its past. Probably 1 or 2 billion years ago, another galaxy fell into Andromeda. The collision scrambled the orbits of stars, displaced the central black hole, and left behind this double nucleus structure. Computer simulations of galaxy mergers can reproduce features like this. When two galaxies collide, their central black holes don't immediately merge. They orbit each other for hundreds of millions of years, slowly spiraling closer. During this time, one black hole can be displaced from the galactic center. Eventually, the black holes merge, but the displaced structure can remain visible for billions of years afterward. The double nucleus we see in Andromeda today is evidence of this violent past. It's a scar from a previous collision, and it's a preview of what might happen to the Milky Way, because Andromeda is going to collide again with us. 2.5 million light-years separate the Milky Way from Andromeda, 15 quintillion miles. What fills that gap? Almost nothing. Intergalactic space contains roughly 1 hydrogen atom per cubic meter. For comparison, Earth's atmosphere at sea level contains about 25,000 trillion atoms per cubic meter. Intergalactic space is 25 orders of magnitude less dense. It's a better vacuum than anything we can create in laboratories on Earth. The atoms that do exist are mostly hydrogen and helium, primordial elements left over from the Big Bang. These have been drifting through the void for 13.8 billion years, spread so thin that an individual atom might travel for millions of years without encountering another. There's also dark matter. We can't see it because it doesn't interact with light, but we know it's there from its gravitational effects. When astronomers measure how fast galaxies rotate, They find they spin too fast based on visible matter alone. The only explanation is invisible mass, providing extra gravity. Dark matter makes up about 85% of all matter in the universe. Everything we can see, stars, planets, gas, dust, people, is the minority. The Milky Way has a dark matter halo extending far beyond its visible edge. Andromeda has an even larger halo, and somewhere in the middle, these halos overlap. There's an invisible bridge of dark matter connecting our galaxies, pulling them together. Occasionally, there are also stray stars in intergalactic space. Stars ejected from their galaxies by gravitational interactions. A star passing too close to a supermassive black hole can be slingshot outward at speeds exceeding 600 miles per second. These orphan stars drift through the void, truly alone. If a planet orbited one of these stars, and if life existed there, they'd see distant galaxies in every direction, impossibly remote. Their nearest neighboring star might be millions of light years away. They would be more isolated than any civilization within a galaxy could ever be. So intergalactic space is mostly vacuum. A few hydrogen atoms per cubic meter, dark matter in diffuse halos, the occasional orphaned star, and vast, almost unimaginable distances. 2.5 million light-years of this near-perfect emptiness separates the Milky Way from Andromeda, but this gap is closing. Andromeda isn't sitting still. It's moving toward us at about 70 miles per second, 245,000 miles per hour. We know this through the Doppler effect. When an object emitting light moves toward you, its light waves compress, shifting toward the blue end of the spectrum. When it moves away, the waves stretch, shifting toward red. Almost every galaxy in the universe shows a redshift because the universe is expanding, carrying galaxies apart. But Andromeda shows a blue shift. It's moving toward us. The expansion of the universe is trying to push Andromeda away, but gravity is stronger at this distance. The mutual gravitational attraction between the Milky Way and Andromeda overwhelms cosmic expansion. Gravity wins. The two galaxies are falling toward each other and have been for billions of years. At 70 miles per second, across 2.5 million light-years, you can calculate when they'll meet. About 4 billion years from now. 4 billion years might sound like forever. It's longer than Earth has been a planet. Longer than life has existed. But on cosmic timescales, it's just around the corner. The collision won't happen all at once. It will unfold in stages over billions of years. And understanding what happens requires understanding what galaxies actually are. When people hear that two galaxies are going to collide, they imagine stars smashing into each other like billiard balls. Explosions, destruction, chaos. But that's not how it works. Galaxies are mostly empty space. The Milky Way contains hundreds of billions of stars, but those stars are separated by light years of emptiness. The Sun is 865,000 miles across. The distance to Proxima Centauri is 25 trillion miles. The Sun occupies less than 1/1,000,000th of the distance to the nearest star. Everything else is vacuum. When two galaxies pass through each other, the stars are so small and so far apart that the probability of any two stars actually colliding is essentially zero. It's like firing two shotgun blasts at each other from a mile away. A few pellets might hit, but most pass through empty space. So, when we say galaxies collide, we don't mean stars collide. We mean the galaxies pass through each other, their gravity scrambling each other's orbits, their gas clouds colliding and triggering starbursts, their structures merging over billions of years into something new. It's a slow, gravitational dance, a reshaping of structure on timescales that dwarf human comprehension. Let's walk through what this actually looks like, step by step, over billions of years. Jump forward 4 billion years from today. The sun has evolved significantly. It's hotter now, brighter, burning through its hydrogen fuel faster than it did in the past. The increased solar output has been heating Earth for hundreds of millions of years. The oceans have begun to evaporate. Water vapor in the atmosphere creates a runaway greenhouse effect, trapping more heat, causing more evaporation. Earth's surface temperature has risen past the point where liquid water can exist. The planet that gave birth to life, that hosted billions of years of evolution, that saw the rise of humanity, and perhaps whatever came after, is dying. If any form of life still exists, it's deep underground, clinging to geothermal vents, or it's migrated elsewhere, perhaps to the outer solar system, to the moons of Jupiter or Saturn. Anywhere the sun's increased output creates habitable conditions. But forget Earth's fate for a moment. Look up at the night sky. Andromeda now dominates your view. What was once a faint smudge, barely visible to the naked eye, is now an enormous spiral structure, stretching across 30 degrees of sky, 60 times the apparent width of the full moon. You can see its central bulge clearly, without any optical aid, a bright yellow-white glow pulsing with the light of hundreds of billions of old stars. You can see the spiral arms swirling outward from the core, great sweeping arcs dotted with blue-white regions where young, hot stars are forming. Dark lanes of dust thread through the arms, silhouetted against the background glow. The entire galaxy has a faint luminescence from billions of older, redder stars that make up most of its mass. It's spectacular, unlike anything humans alive today will ever see, and it's getting larger every year, not fast enough to notice from one night to the next. But if you could compare photographs taken a decade apart, the difference would be obvious. Andromeda is growing, approaching, looming. At this stage, Andromeda is still about 600,000 light-years away. That's 6 times the diameter of the Milky Way. Still, a vast distance. Still, intergalactic space. But no longer the 2.5 million light-years it was at the beginning. The galaxies have been falling toward each other for 4 billion years, and they've crossed most of that gap. Even though they're still hundreds of thousands of light-years apart, they're already beginning to influence each other gravitationally. The mutual gravitational pull between them is starting to have visible, measurable effects. Both galaxies are developing tidal tails. Let me explain what this means and why it happens. Gravity decreases with distance. The farther you are from a massive object, the weaker its gravitational pull. This is why Earth orbits the Sun but isn't pulled into it. We're far enough away that the Sun's gravity only pulls hard enough to keep us in orbit, not to drag us inward. But this means that different parts of an object experience different amounts of gravitational force if they're at different distances from the source. Consider the Milky Way. A star on the edge of the Milky Way, closest to Andromeda, is about 550,000 light-years from Andromeda's center. A star at the Milky Way's center is about 600,000 light-years from Andromeda. A star on the opposite edge of the Milky Way, the side farthest from Andromeda, is about 650,000 light-years away. These differences might seem small compared to the total distance, but they matter. The stars closest to Andromeda feel a stronger gravitational pull than the stars at the Milky Way's center, and stars at the center feel more pull than stars on the far side. This difference in gravitational force across the galaxy is what creates tidal forces. The result is stretching. The stars closest to Andromeda get pulled harder than the galactic average and start to move ahead. They form a bulge, extending toward Andromeda. The stars on the far side, feeling less pull, start to lag behind. They form a tail stretching away from Andromeda. The galaxy is being stretched like taffy. The same thing happens to Andromeda. It's being stretched by the Milky Way's gravity. A bulge toward us, a tail away from us. As the galaxies continue approaching, these tidal tails grow longer and more prominent. They stretch for tens of thousands of light years at first. Then, hundreds of thousands. Eventually, they extend for millions of light years, long, graceful streams of stars pulled away from their parent galaxies. But here's something counterintuitive. The tidal tails don't point directly toward or away from the other galaxy. They curve. This happens because the galaxies aren't just pulling on each other, they're also rotating. Each galaxy spins, completing one rotation every few 100 million years. As they pull on each other, their rotation causes the tidal tails to curve like water spiraling down a drain. Computer simulations of galaxy mergers show these curved tidal tails forming naturally. Modern simulations can track billions of particles, each representing a clump of stars or dark matter. The simulation calculates how gravity affects each particle's trajectory. When you run these simulations for billions of simulated years, compressed into hours of computing time, you see the tidal tails emerge, grow, curve, and eventually wrap around the merging galaxies in complex patterns. These simulations have been refined over decades. In the 1970s and 80s, astronomers ran simple simulations with just a few thousand particles and limited physics. Today, with modern supercomputers, we can simulate mergers with billions of particles. We can track not just the stars, but also the gas, the dust, and the dark matter. We can model star formation, supernova feedback, black hole growth. We can watch how galaxies evolve over billions of years. And what these detailed simulations show is that galaxy mergers follow predictable patterns. The tidal tails always form. The spiral structure always dissolves. The gas always collides and triggers starbursts. The final product is always an elliptical galaxy. The details vary, depending on the masses, the impact angle, the rotation rates. But the overall pattern is consistent. Jump forward another few 100 million years. We're now about 3.3 billion years from today. The tidal tails are very prominent now. Both galaxies look distorted, stretched, pulled out of their neat spiral shapes. Long streams of stars arc outward from each galaxy, glowing faintly against the darkness of intergalactic space. From Earth's perspective, if Earth still exists, and if anything is there to observe, the night sky is transforming. The Milky Way band that has stretched across human skies for all of history is changing shape. It's no longer a neat band. It's becoming broader, more diffuse, with bright knots where the galactic core and spiral arms used to be. And Andromeda now fills a huge portion of the sky, 40 degrees across, 80 times the apparent width of the full moon, so large that you can't take it in all at once. You have to turn your head to see from one edge to the other. The spiral arms are clearly visible as distinct structures. You can see the bright HII regions, clouds of ionized hydrogen, lit up by young stars dotted throughout the arms like glowing jewels. You can see the dark dust lanes threading between the arms. You can see the central bulge, so bright now that it casts faint shadows on Earth's surface during the night. And now, finally, the outer edges of the two galaxies begin to overlap. This is first contact. The moment when stars from one galaxy actually enter the space occupied by the other galaxy. It's not a sharp boundary. Galaxies don't have edges like a table or a wall. They gradually fade out, becoming less and less dense until you can't really say where the galaxy ends and intergalactic space begins. But there's definitely a point where you can say the galaxies are now occupying the same space. The outermost stars of Andromeda, the stars in its extended halo and tidal tail, are now mingling with the outermost stars of the Milky Way. These are still separated by light years, still not in danger of actually colliding, but they're now part of the same gravitational system, orbiting around the combined center of mass of both galaxies. From Earth, the night sky becomes absolutely spectacular. Instead of one faint Milky Way band, you see two distinct structures crossing the sky. One is the remaining core of the Milky Way, still recognizable but distorted, no longer a neat spiral but a chaotic distribution of stars. The other is Andromeda's core, now so close that individual bright stars within it are visible to the naked eye. Between the two cores, you see chaos. Stars from both galaxies are mixed together, creating a complex, turbulent structure that defies easy description. Bright blue regions dot the sky. These are the starburst regions we'll discuss in detail shortly. They look like glowing clouds, some as large as the full moon, visible even in daylight as faint blue patches. Dark lanes of dust thread through everything, silhouetted against the background glow. The combined light from both galaxies' cores is so bright that true darkness never falls. Even at midnight, the sky has a faint glow, like perpetual twilight. But here's the remarkable, almost anticlimactic thing. If you were standing on Earth's surface at this moment, assuming Earth still exists in any recognizable form, you probably wouldn't notice anything unusual in your daily life. The sky would look spectacular at night, yes. But during the day, the sun would still rise and set on schedule. The seasons would still change, driven by Earth's axial tilt. The temperature wouldn't suddenly spike or plummet. Life, if any existed, would go on as normal. That's because, even though the galaxies are colliding, even though first contact has occurred, the distances between individual stars are still enormous. The nearest stars from Andromeda are probably still dozens or hundreds of light years away. There's no immediate danger of a stellar collision. No radiation surge that would sterilize the planet. No gravitational disruption that would tear Earth from its orbit. Just a slowly, gradually changing night sky. The threat to Earth isn't the collision itself. It's the sun's natural evolution, which has made the planet uninhabitable. The galactic collision is a spectacle, not a danger, at least not on human timescales. But the galaxy as a whole is feeling profound effects. The sun's orbit around the galactic center, which has been stable and roughly circular for 4.6 billion years, is now changing dramatically. Andromeda's gravity is pulling on everything in the Milky Way. Not evenly, but with varying strength, depending on position. This creates torques, accelerations, complex gravitational interactions. Orbits that were circular are becoming elliptical. Orbits that were in the galactic plane are tilting out of it. Stars that were moving together in an organized flow are being scattered. Some stars are being pulled toward Andromeda, accelerating as they fall toward the combined center of mass. Others are being flung outward, away from both galaxies. Their orbital velocity increased to the point where they escape the merged system entirely. These escaping stars become intergalactic wanderers, orphaned from their home galaxy, drifting through the void forever. And some stars, including possibly our Sun, are having their orbits scrambled without being ejected. They're kicked into new paths that are more elliptical, more tilted, more erratic than their original orbits. This orbital scrambling is one of the main effects of a galaxy merger. It's what transforms a spiral galaxy into an elliptical galaxy. Before the collision, most stars in a spiral galaxy like the Milky Way follow fairly circular orbits around the galactic center. They all move in roughly the same plane, the galactic disk. They all orbit in the same direction. This organized, coherent motion is what creates and maintains the spiral structure. The spiral arms exist because density waves move through the disk, regions where stars and gas pile up temporarily as they orbit. It's like a traffic jam on a highway. The cars move through the jam, but the jam itself persists in the same location because new cars keep entering as old cars leave. Spiral arms work the same way. Stars move through them, but the arms persist because new stars keep entering as old stars leave. But when you add the gravitational influence of another galaxy, that organization breaks down. Stars get kicked into new orbits that no longer lie in the galactic plane. Some orbit clockwise, some counterclockwise. Some have highly elliptical orbits that take them far from the galactic center and back. The orbits become randomized, three-dimensional, chaotic, and when orbits are randomized like this, spiral structure can't exist. There's no coherent rotation to maintain density waves. The result is an elliptical galaxy, a smooth, featureless distribution of stars orbiting in random directions. The gas between the stars is affected even more dramatically than the stars themselves. And this is where things get visually spectacular. Stars orbit through space without interacting much because they're so small and so far apart. Two stars can pass within a light year of each other and never know the other existed. But gas is different. Gas fills space. It's diffuse. Yes, only a few atoms per cubic centimeter in most regions, but it occupies volume, and gas can collide. When two clouds of gas moving in different directions meet, they don't pass through each other. They slam together. The collision compresses the gas, squeezing it into a smaller volume. Compression heats the gas. This is basic thermodynamics, the same principle that heats up a bicycle pump when you use it. The collision also creates shock waves, regions where the gas is compressed to much higher densities than usual. These shock waves propagate through the colliding clouds like ripples on a pond. And here's where star formation comes in. Stars form when gas becomes dense enough and cold enough that gravity can pull it together into a collapsing cloud. Under normal conditions in a galaxy, gas is too diffuse and too hot for this to happen easily. Star formation proceeds slowly, at a steady pace. In the Milky Way today, about 1 or 2 stars form per year on average. But when gas clouds collide during a galaxy merger, conditions change dramatically. The collision compresses the gas, increasing its density by factors of 10, 100, sometimes 1,000. The shock waves compress it even further in localized regions. And while the collision initially heats the gas, the increased density allows it to radiate that heat away more efficiently. Dense gas cools faster than diffuse gas because there are more atoms to radiate energy. The result is gas, that's both denser and cooler than normal, exactly the conditions needed for rapid star formation. And so stars begin forming at a dramatically increased rate, not one or two per year, but hundreds or thousands per year. This is called a starburst. A galaxy undergoing a starburst can form more stars in a few million years than it would normally form in a billion years. The entire galaxy lights up with new stars, especially young, hot, massive stars that burn blue and bright. These massive stars, stars with 10, 20, 50 times the mass of the Sun, live fast and die young. They burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion-year lifespan. Then they explode as supernovas, releasing enormous amounts of energy and scattering heavy elements into space. The supernova explosions trigger even more star formation by compressing nearby gas clouds. It becomes a feedback loop. Gas collides, stars form, massive stars explode, explosions compress more gas, more stars form, a frenzy of creation. Jump forward to about 2.7 billion years from today, roughly halfway through the collision timeline. The starburst is in full swing now. The Milky Way and Andromeda have passed through each other for the first time. Their cores have separated again, moving apart after the initial interpenetration. But they're not done. Gravity is still pulling them together. The tidal tails have stretched enormously, some extending over 1 million light-years into space. And throughout both galaxies, star formation is occurring at rates hundreds of times higher than normal. From Earth, if anything remains there to observe, the night sky would be dominated by these star-forming regions. They appear as vast nebulas, clouds glowing in brilliant reds and blues. The red comes from hydrogen emission, hydrogen atoms absorbing energy from nearby hot stars and re-emitting it as red light. The blue comes from scattered light from the hot stars themselves. Some of these nebulas span hundreds of light-years and contain enough gas to form millions of stars. They'd be visible across the galaxy, beacons of creation amid the chaos. Within these nebulas, you'd see dark pillars and columns. These are regions where dense gas is resisting the erosive effects of stellar winds and radiation from nearby young stars. The hot stars surrounding these pillars emit intense ultraviolet light and powerful stellar winds. This radiation heats the surface of the pillars, causing gas to evaporate. But the densest parts resist evaporation and remain intact, casting shadows in the ultraviolet light. The result is a pillar of dense gas carved by radiation, often with new stars forming deep inside where the gas is densest. These pillars are stellar nurseries, similar to the famous Pillars of Creation in the Eagle Nebula, but much larger and more numerous. Some would be truly enormous, tens or hundreds of light-years tall, visible from across the galaxy as dark silhouettes against glowing nebulas. But this burst of star formation is a double-edged sword. It's beautiful, creating spectacular nebulas and brilliant clusters of young stars. But it's also dangerous. Massive stars produce intense radiation. Ultraviolet light, X-rays, high-energy particles. If a planet happens to be near a starburst region, it gets bathed in this radiation. Ultraviolet light can strip away atmospheres over time. X-rays can break apart complex molecules, making chemistry difficult or impossible. High-energy particles can damage DNA and other biological molecules. For existing life, especially complex life that's adapted to stable conditions, a nearby starburst could be catastrophic. Earth's ozone layer, which protects life from ultraviolet radiation, could be destroyed. The radiation could sterilize the surface. Even life deep in the oceans or underground might struggle as the radiation disrupts ecosystems from the top down. On the other hand, this burst of star formation also creates new opportunities. New stars mean new planetary systems. Billions of new planets forming around billions of new stars. If any of those planets end up in habitable zones around stable stars, and if conditions are right, life could emerge. The merger might destroy existing life, but it also seeds the galaxy with countless new chances for life to begin. In that sense, galaxy mergers are both destructive and creative. They're moments of transformation, where old structures break down and new possibilities emerge. Jump forward another 600 million years to about 2.1 billion years from today. The galaxies have separated after their first pass. They're now about 400,000 light-years apart, but they're not moving apart anymore. Their mutual gravity has slowed their separation to zero. And now, they're starting to fall back together. This is the beginning of the second pass. The second pass is often more violent than the first, because by this point, both galaxies have been severely disrupted. Their spiral structures are completely gone, replaced by chaotic, amorphous distributions of stars. Their gas has been compressed, heated, and partially consumed by the first burst of star formation. And now, they're falling back together, accelerating as gravity pulls them inward. The relative velocity at closest approach during the second pass can be even higher than during the first pass, because the galaxies are falling from a shorter distance. It's like dropping a ball from 10 feet versus dropping it from 5 feet. The ball dropped from 10 feet has more time to accelerate and hits the ground faster. Similarly, galaxies falling from a greater distance have more time to accelerate and pass through each other faster. During the second pass, the galaxies interpenetrate more deeply. Their cores come closer together. More stars get scattered. More gas gets compressed. The starburst intensifies, triggering even more star formation, even more supernovas. The tidal tails, which had stretched outward during the first pass and the subsequent separation, now curve back. They wrap around the merging galaxies like tentacles, forming complex, graceful patterns. Some stars in the tidal tails fall back into the main body of the merged system. Others escape entirely, flung out into intergalactic space by the violent gravitational interactions. These ejected stars become intergalactic wanderers. They're no longer bound to any galaxy. They drift through the void, billions of light years from the nearest major galaxy, truly alone in the universe. If any of these ejected stars have planets, and if any of those planets harbor life, those civilizations would have a profoundly different view of the cosmos. Their night sky wouldn't show the Milky Way or any other galaxy from the inside. Instead, they'd see distant galaxies in all directions, each one a faint smudge of light, billions of light years away. They'd be orphans, cut off from the galaxy that birthed their star, drifting through emptiness forever. The second pass is followed by a third pass, then a fourth, each one bringing the cores closer together, each one further scrambling the orbits of stars. With each pass, the galaxies lose energy. Not because energy disappears, energy is always conserved, but because organized kinetic energy is converted into random kinetic energy. The galaxies are initially moving toward each other with a lot of organized motion. All the stars in each galaxy moving together as a unit. But as they interact gravitationally, this organized motion gets randomized. Stars get kicked into different orbits. Some speed up, some slow down, but the average kinetic energy decreases because energy goes into escaping stars and tidal heating. This process is called dynamical friction, and it causes the galaxies to spiral closer together with each pass. Eventually, after 3, 4, maybe 5 passes, spanning several billion years, the two galactic cores merge. They settle into a single, stable configuration, one galaxy where there used to be two. Jump forward to about 8 billion years from today, 4 billion years after the collision began. The merger is complete. Milkdromeda has formed. The name is a portmanteau of Milky Way and Andromeda. Some astronomers prefer Milkdromeda, but Milkdromeda seems to have stuck. Milkdromeda is an elliptical galaxy. It's roughly spherical or slightly football-shaped, about 200,000 light-years in diameter. It contains roughly 1.4 trillion stars. All the stars from the Milky Way, all the stars from Andromeda, minus the ones that were ejected during the merger. The mass is about 4 trillion solar masses when you include dark matter. At its center sits a supermassive black hole weighing about 104 million solar masses. This is the combined mass of Sagittarius A star and Andromeda's central black hole after they merged. The merger of the central black holes deserves special attention because it's one of the most violent events the universe can produce. When two supermassive black holes merge, they don't do it quietly. To understand what happens, we need to back up and track how the two black holes come together. At the beginning of the collision, Sagittarius A star sits at the center of the Milky Way, and Andromeda's black hole sits at the center of Andromeda. They're separated by 2.5 million light-years. As the galaxies approach each other, the black holes approach too, carried along with their respective galactic cores. But even after the galaxies have merged, even after the stars have been scrambled and mixed, the black holes don't immediately merge. They end up orbiting each other. Think about what happens during the merger. The two galactic cores pass through each other, then separate, then pass through again. With each pass, they come closer. Eventually, they end up orbiting around their common center of mass, separated by maybe a few hundred or a few thousand light-years. Two supermassive black holes, one weighing 4 million solar masses, the other weighing 100 million solar masses, circling each other like a binary star system. But unlike stars, black holes don't shine. You can't see them directly. You can only infer their presence by watching how nearby stars and gas behave. As the black holes orbit each other, they gradually spiral closer. This happens because they emit gravitational waves. Gravitational waves are ripples in space-time itself, predicted by Einstein's general theory of relativity in 1916. Einstein showed that when massive objects accelerate, they create disturbances in the fabric of space-time that propagate outward at the speed of light. It's similar to how accelerating electric charges create electromagnetic waves, light. But gravitational waves are much, much weaker than electromagnetic waves. You need truly enormous masses moving at high speeds to create detectable gravitational waves. Two black holes orbiting each other qualify. As they orbit, they emit gravitational waves continuously. These waves carry energy away from the system, and because energy is conserved, the black holes must lose energy. They do this by moving closer together and orbiting faster. It's counterintuitive. Losing energy makes them speed up, but it makes sense from an orbital mechanics perspective. As objects in orbit lose energy, they drop to lower orbits. Lower orbits are faster. So the black holes spiral inward, accelerating as they go. Initially, when they're separated by thousands of light-years, this spiraling is extremely slow. It might take hundreds of millions or even billions of years for them to get significantly closer. But as they approach each other, the gravitational wave emission increases. The closer they are, the faster they orbit. The faster they orbit, the more gravitational waves they emit. The more gravitational waves they emit, the faster they spiral together. It becomes a runaway process. When they're separated by just a few light years, the spiral accelerates dramatically. When they're separated by light months, they're orbiting each other hundreds of times per second. The gravitational waves they're emitting at this point are intense, carrying away energy at a staggering rate. And then, finally, they merge. The actual merger takes less than a second. One moment, there are two distinct black holes orbiting each other at nearly the speed of light. The next moment, they collide, their event horizons touching and merging into one. The merged black hole vibrates violently, its event horizon oscillating like a struck bell. It emits a final burst of gravitational waves as it settles into a stable configuration. This final burst is called the ringdown, and it contains information about the mass and spin of the final black hole. The total energy released during this merger is staggering. In the final second before merger, the two black holes can emit more energy in gravitational waves than all the stars in the observable universe are emitting in electromagnetic radiation. Think about that. 2 trillion galaxies, each containing hundreds of billions of stars, all shining together. The gravitational wave emission from two merging supermassive black holes exceeds that. Of course, that energy is emitted as gravitational waves, not light, so you can't see it with your eyes or with a telescope. But you can measure it with gravitational wave detectors. The first gravitational waves ever detected by humans came from a black hole merger. On September 14, 2015, the LIGO detectors in Louisiana and Washington State registered a gravitational wave signal. The signal lasted less than a second. It represented two stellar mass black holes, weighing 29 and 36 solar masses, merging 1.3 billion light-years away. The collision happened 1.3 billion years ago. The gravitational waves traveled through space for 1.3 billion years before reaching Earth. When they arrived, they stretched and compressed space itself by an amount smaller than 1/10,000th the diameter of a proton. LIGO detected this impossibly tiny distortion. The final black hole weighed 62 solar masses. 3 solar masses worth of energy was converted into gravitational waves, according to Einstein's E equals mg squared. That's the equivalent of converting 3 entire suns into pure energy in a fraction of a second. For supermassive black holes like Sagittarius A star and Andromeda's black hole, the energy release would be proportionally larger. Millions of solar masses worth of energy, all released as gravitational waves in the final moments before merger. If humanity still exists when this happens, if we have gravitational wave detectors operating billions of years from now, we'll be able to observe this merger. We'll measure the gravitational waves as they pass through Earth, causing space-time itself to stretch and compress by tiny amounts. We'll extract information about the black hole masses, their spins, their orbital parameters. We'll watch, in a sense, as two black holes merge into one, right in our cosmic backyard. It will be one of the most significant astronomical observations ever made. Milkdromeda will look nothing like its parent galaxies. Where the Milky Way and Andromeda were both beautiful spirals with organized structure, Milkdromeda is smooth and featureless. There are no spiral arms, no central disk, no organized rotation. just a smooth distribution of stars, densest at the center and gradually fading toward the edges. The stars orbit in random directions. Some orbit clockwise, some counterclockwise. Some have circular orbits, some highly elliptical. Orbits are tilted at all possible angles. It's a three-dimensional swarm, not a two-dimensional disk. This is typical of elliptical galaxies. They're the end products of galaxy mergers. The random orbits are what give them their elliptical shape. Stars moving in all directions create a roughly spherical or football-shaped distribution. Most of the star formation has ceased by this point. The initial starburst consumed much of the available gas. Supernova explosions heated and dispersed more gas. Some gas was ejected from the galaxy entirely by the violence of the merger. What remains is mostly too hot and diffuse to form new stars. Milkdromeda will be dominated by old stars. Red dwarfs that will burn for trillions of years. Sun-like stars in their middle age or approaching the end of their lives. Red giants and white dwarfs. The massive blue stars that formed during the starburst are long gone, having exploded as supernovas millions or billions of years ago. The galaxy has a reddish color overall, the color of old stellar populations. It's not dead, exactly. Stars continue to shine. Planets continue to orbit. Life, if it exists, continues to live, but the galaxy has settled into a quiet, mature state. The frenzy of the merger is over. The chaos has resolved into a new equilibrium. But here's the central question that's been building throughout this entire story. Could we ever reach Andromeda before the merger happens? Could humanity, or whatever we evolve into, ever make the journey across 2.5 million light-years to visit this galaxy before it merges with our own? Could we establish a presence there, explore it, study it up close? The answer reveals something profound about the universe, something about the boundaries that physics imposes on all possible futures. The answer is no. Not just difficult, no. Not someday. With better technology, no. Impossible, no. And understanding why requires understanding the limits that nature has built into the fabric of reality. Let's start with what we've actually achieved. We've sent exactly 5 spacecraft beyond the solar system. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. All launched between 1972 and 2006. All still traveling outward. Voyager 1, launched in 1977, is currently the most distant. It's now about 15 billion miles from Earth, traveling at about 38,000 miles per hour relative to the Sun. To put that in perspective, that's roughly 10.5 miles per second, or about 0.005% the speed of light. After 47 years of continuous travel, Voyager has covered about 0.002 light-years. The distance to Proxima Centauri is 4.24 light-years. At Voyager's current speed, it would take about 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. And Proxima Centauri is our nearest stellar neighbor. Andromeda is 2.5 million light-years away. At Voyager's speed, the journey would take over 42 billion years. That's 3 times the current age of the universe. By the time Voyager reached Andromeda at its current speed, the universe itself would be ancient beyond recognition. Most stars would be dead. Galaxies would be dispersed. The universe would be a cold, dark place, bearing no resemblance to the universe we see today. But Voyager is old technology. built with 1970s electronics and propulsion systems. Surely we can do better. What's the fastest spacecraft we've ever built? That would be the Parker Solar Probe, launched in 2018 to study the Sun. The Parker Solar Probe uses a series of Venus gravity assists to dive closer and closer to the Sun with each orbit. At its closest approach, which occurred in December 2024, it reached speeds of about 430,000 miles per hour relative to the Sun. That's about 119 miles per second, or 0.064% the speed of light, roughly 13 times faster than Voyager. At Parker Solar Probe speeds, the journey to Andromeda would still take roughly 3.9 billion years. Better than Voyager, but still longer than the current age of Earth. Still impossibly long. What if we really pushed the limits of known physics and engineering? What if we built a spacecraft that could travel at 1% the speed of light? 1% of light speed is about 1.8 million miles per hour, or about 1,860 miles per second. This is about 16 times faster than Parker Solar Probe's maximum speed. Achieving this would require revolutionary propulsion technology, nuclear pulse propulsion, where you detonate nuclear bombs behind your spacecraft and ride the shockwave forward. The concept was actually studied seriously in the 1950s and 60s under Project Orion. Engineers calculated that a spacecraft using nuclear pulse propulsion could theoretically reach several percent of light speed. Or fusion rockets, where you fuse hydrogen into helium and use the energy released to accelerate. This is how stars work, and if we could harness fusion for propulsion, it would be far more efficient than chemical rockets, or antimatter rockets, where you annihilate matter with antimatter and direct the energy backward. Antimatter annihilation converts 100% of mass into energy, making it the most efficient possible fuel. All of these are theoretically possible, but require technology far beyond anything we have today. At 1% of light speed, the journey to Andromeda would take 250 million years. That's still an unimaginably long time. Longer than dinosaurs have been extinct. Longer than mammals have existed. But at least it's conceivable that technology could survive that long if properly maintained. What if we pushed even harder? 10% of light speed. About 18 million miles per hour. Now we're talking about truly exotic propulsion systems, perhaps a laser sail, where enormous lasers on Earth or in orbit push a spacecraft equipped with a reflective sail. The Breakthrough Starshot project, announced in 2016, proposes exactly this for reaching Proxima Centauri. The idea is to build ground-based or space-based lasers with combined power in the gigawatts or even terawatts. These lasers would push a tiny spacecraft, maybe just a few grams, equipped with a reflective sail. The spacecraft could potentially reach 20% of light speed, making the journey to Proxima Centauri in about 20 years. For Andromeda, you'd need to scale this up dramatically. At 10% of light speed, the journey takes 25 million years. Still, a geological timescale. Still far beyond any conceivable human mission. But at least we're getting into a time frame where you might imagine a self-repairing, autonomous spacecraft making the journey. Let's go even faster. Half the speed of light. 93 million miles per hour. 335 million miles per hour. At this speed, the trip to Andromeda takes 5 million years. This is where things start to get truly strange because of special relativity. Time dilation begins to become significant. Let me explain what this means. Special relativity, developed by Einstein in 1905, tells us that time is not absolute. Time passes at different rates for observers moving at different speeds. This isn't science fiction or speculation. It's observed fact, confirmed by countless experiments over more than a century. GPS satellites orbit Earth at about 8,700 miles per hour. At this speed, time passes slightly slower for the satellites than it does on Earth's surface. The difference is only about 7 microseconds per day, but it's real and measurable. If GPS satellites didn't account for this time dilation, along with gravitational time dilation from general relativity, the system would accumulate positioning errors of several miles per day. GPS works because we correct for relativistic time dilation. In particle accelerators, we see subatomic particles moving at 99.99% of light speed. These particles are unstable and would normally decay in microseconds. But because they're moving so fast, time passes more slowly for them from our perspective. They live hundreds of times longer than they should, allowing us to detect them. This is called time dilation, and it's a fundamental feature of how time works in our universe. The faster you move, the slower time passes for you relative to a stationary observer. At everyday speeds, the effect is negligible. If you drive across the country at 60 miles per hour, you age about 1 nanosecond less than if you had stayed home. Completely unmeasurable, without atomic clocks, but at high speeds, the effect becomes significant. At 50% of light speed, time passes at about 87% the normal rate. 1 year of your time corresponds to 1.15 years for someone at rest. At 90% of light speed, time passes at about 44% the rate for a stationary observer. 1 year of your time corresponds to 2.3 years for someone at rest. At 99% of light speed, time passes at about 14% the normal rate. 1 year for you equals 7 years for someone at rest. At 99.9% of light speed, time passes at about 4.5% to the normal rate. 1 year for you equals roughly 22 years for someone at rest. So, here's where it gets interesting for interstellar travel. If you could somehow accelerate to 99% of light speed, the trip to Andromeda would take 2.5 million years from Earth's perspective. But from your perspective on the spacecraft, with time passing at 14% the normal rate, the journey would only take about 350,000 years of subjective time. Still impossibly long for a human lifespan, but dramatically shorter than the external time. If you could reach 99.9% of light speed, time would pass at about 4.5% in the normal rate. The 2.5 million year journey from Earth's perspective would take only about 112,000 years from your perspective. At 99.99% of light speed, your subjective journey time drops to about 35,000 years. At 99.999%, about 3,500 years. Still far too long for any individual, but now you're in a time frame where you might imagine a generation ship making the journey. But here's the crucial point. You can't actually reach these speeds. Not with any technology we can imagine. The problem is energy. As you accelerate toward light speed, your effective mass increases. This is a consequence of special relativity, and it's been confirmed by countless particle accelerator experiments. The faster you move, the more energy it takes to accelerate you further. At 90% of light speed, your effective mass is about 2.3 times your rest mass. At 99% of light speed, it's about 7 times your rest mass. At 99.9%, it's about 22 times your rest mass. This means it takes 22 times as much energy to accelerate you from 99.8% to 99.9% as it took to accelerate you from 0 to 90%. And it keeps getting worse exponentially as you approach light speed. To actually reach light speed would require infinite energy, which means it's impossible. Nothing with mass can reach light speed. This isn't a technological limitation. It's a law of physics. You can't engineer around it. You can't invent a better rocket. The universe simply doesn't allow it. Let's put some numbers on this to see just how absurd the energy requirements become. Suppose you want to send a small spacecraft, say 1,000 kilograms, to Andromeda at 99% the speed of light. How much energy does that require? The kinetic energy formula in special relativity is more complex than the classical formula you learn in school, but it works out to about 4.5 times 10 to the 21 joules. That's 45 sextillion joules, or 45 zettajoules. For comparison, total human energy consumption in 2023 was about 600 exajoules, or 6 times 10 to the 20 joules. So, accelerating a 1-ton spacecraft to 99% of light speed requires about 75 times all the energy humanity used in an entire year. And that's just to accelerate it. If you want to slow down when you arrive at Andromeda, so you can actually explore instead of shooting past at 99% of light speed, you need the same amount of energy again for deceleration. So, you're looking at 150 years worth of total human energy output just to send a 1-ton probe to Andromeda and have it stop when it gets there. Now, imagine you want to send a generation ship, a spacecraft large enough to house hundreds or thousands of people, a spacecraft with life support, agriculture, manufacturing, recreation, radiation shielding, propulsion systems, everything needed for a multi-thousand-year journey. You're probably looking at a ship massing millions of tons, possibly tens of millions. The energy requirements scale linearly with mass. A 1,000,000-ton ship requires 1,000,000 times more energy than a 1-ton ship. We're now talking about energies equivalent to total human civilization. Energy output over millions of years, all delivered as kinetic energy to a single spacecraft. It's simply not feasible with any energy source we can imagine. And this assumes perfect conversion of energy into kinetic energy with no losses, which is physically impossible. In reality, any propulsion system is inefficient. Rockets, for instance, have to carry fuel, and that fuel has mass, and accelerating that mass requires even more fuel, which has more mass, in an exponential relationship called the tyranny of the rocket equation. The rocket equation tells us that for chemical rockets, reaching even a tiny fraction of light speed is effectively impossible because the fuel requirements grow exponentially. To reach just 1% of light speed with a chemical rocket would require a fuel-to-payload ratio of over 10 to the 100, meaning you'd need more fuel than there are atoms in the observable universe. Even advanced concepts like nuclear pulse propulsion or fusion rockets struggle with the rocket equation at relativistic speeds. You can do better than chemical rockets, but you still run into fundamental limits. Some people suggest using laser sails to get around the rocket equation. The idea is to leave the power source behind, build enormous lasers on Earth or in orbit around the Sun. Equip your spacecraft with a huge, ultra-lightweight, reflective sail. The lasers push the sail, accelerating the spacecraft without it having to carry fuel. This potentially solves the rocket equation problem because the spacecraft mass stays constant. You're not burning fuel. but it introduces new problems that may be even harder to solve. First, you need absurdly powerful lasers. To accelerate even a small probe to relativistic speeds within a reasonable time frame, you need lasers with power outputs measured in gigawatts, terawatts, or even petawatts. For comparison, a large nuclear power plant produces about 1 gigawatt. Total human electricity generation is about 3 terawatts. So you're talking about building laser systems with power outputs comparable to or exceeding all of human civilization's power generation, and sustaining that power for years or decades to accelerate a spacecraft. Second, the lasers have to stay focused on a tiny sail over distances of light years. This is harder than it sounds. Light diffracts. It spreads out as it travels. Even a perfectly collimated laser beam will spread due to fundamental physics. By the time the light travels a light year, even with perfect optics, the beam will have spread to hundreds or thousands of miles in diameter. Most of the laser energy misses the sail entirely and is wasted. You could use a larger sail to capture more of the beam, but larger sails have more mass, making them harder to accelerate. There are clever proposals involving enormous Fresnel lenses positioned at various points in the solar system to refocus the beam, or phased laser arrays that can adjust for diffraction. But all of these require engineering on scales we can barely imagine. Third, even if you solve the power and focusing problems, a laser sail can only accelerate. It can't decelerate unless there's a second laser system at the destination to slow you down. Who's going to build and maintain a petawatt laser system in Andromeda to slow down your spacecraft when it arrives? The spacecraft itself can't carry a laser powerful enough because that would require enormous amounts of power and mass, defeating the whole purpose of the laser sail. Some proposals suggest using the sail to reflect light from stars at the destination for braking, but the geometry is extremely tricky and the deceleration would be very gradual, taking potentially millions of years. What about more exotic solutions like wormholes or warp drives? These show up in science fiction all the time as ways to travel faster than light or to bypass the vast distances of space. Wormholes are hypothetical tunnels through space-time connecting distant points. If they existed, you could potentially enter a wormhole near Earth and exit near Andromeda, bypassing the intervening 2.5 million light-years of space. The trip might take minutes instead of millions of years. Warp drives, as popularized by Star Trek, would create a bubble of space-time around your ship. The bubble moves faster than light while you remain stationary inside it, surfing through space without actually moving. Do these violate the cosmic speed limit? Technically, no. The speed of light limit says that nothing can move through space faster than light. But it doesn't say space itself can't move, or that space-time can't have shortcuts. So, in principle, wormholes and warp drives don't violate relativity as usually stated. In practice, there are enormous problems that probably make both impossible. Wormholes, if they can exist at all, require exotic matter with negative energy density to keep them open. Negative energy density means the energy is less than the energy of empty vacuum. We've observed negative energy density in tiny amounts in quantum systems. The Casimir effect demonstrates this. But creating enough negative energy to hold open a wormhole large enough to send a spacecraft through would require energy scales we can't even estimate. It might require the energy equivalent of an entire star concentrated in a small region, or the mass energy of an entire galaxy. We simply don't know, and we have no idea how to create or manipulate negative energy on macroscopic scales. Beyond that, even if you could create a wormhole, you probably can't use it to travel backward in time. And if you can't travel backward in time, then the wormhole can't connect any two points that weren't already in causal contact. The mathematics of general relativity is complex, but most solutions that include traversable wormholes also include restrictions that prevent causality violations. Essentially, you can't use a wormhole to get anywhere you couldn't have reached by traveling slower than light, given enough time. Warp drives have similar problems. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is the most famous warp drive concept. It requires negative energy density to create the warp bubble, just like wormholes. Same problem. We don't know how to generate negative energy on the scales needed. Calculations suggest the energy requirements for an Alcubierre drive are enormous, perhaps equivalent to the mass energy of Jupiter or larger. Even if you could somehow gather that much energy, you'd need to arrange it in a specific configuration with negative energy density, which we don't know how to do. Beyond the energy problem, there are causality issues. If you can travel faster than light in one reference frame, special relativity says you can potentially travel backward in time in another reference frame. This leads to paradoxes, the possibility of going back and killing your grandfather before your father was born, that sort of thing. Most physicists believe the universe simply doesn't allow causality violations, which means faster than light travel is impossible, even via warp drives or wormholes. The laws of physics conspire to prevent it. So we're left with generation ships as the only remotely plausible option for reaching Andromeda. If we can't travel faster than light, and if we can't reach even a significant fraction of light speed with conceivable technology, then the only way to reach Andromeda is to build a spacecraft that travels for millions of years, a mobile habitat, a self-contained world capable of sustaining human life, or whatever comes after humans, for timescales longer than recorded history. The original crew would live their entire lives on the ship. They'd have children. Those children would grow up knowing nothing but the ship, having never seen Earth or any planet. They'd have their own children and die. Generation after generation, living and dying aboard the ship, until finally, millions of years later, distant descendants arrive at Andromeda. At a realistic speed, say 0.01% of light speed, which is roughly 18.5 miles per second, about the speed of Earth's orbit around the Sun, and achievable with advanced fusion or nuclear pulse propulsion, the journey would take 2.5 billion years. 2.5 billion years. That's 62 million generations if we assume a 40-year generation time. 62 million generations of people born on the ship, living their entire lives on the ship, dying on the ship, never seeing the destination, never knowing anything but endless travel through the void. The descendants who arrived would be so far removed from the original crew that they'd have no memory of Earth, no connection to humanity's origins, no understanding of why they're on this ship or where it came from. Their culture would have evolved beyond recognition. Their language would be unrecognizable to the original crew. Their biology might have evolved significantly. 2.5 billion years is enough time for dramatic evolutionary changes. Life on Earth went from single-celled organisms to complex multicellular life in less time than that. They might not even be the same species anymore. And this all assumes the ship can function for billions of years without critical failures. It assumes materials don't degrade, systems don't break down, and everything can be maintained or replaced indefinitely. It assumes the crew can maintain technology they didn't build, operating systems they might not fully understand, fixing problems in equipment that's been running for millions of years. It assumes they can maintain purpose and direction over timescales longer than all of recorded human history by factors of millions. These are extraordinary, probably impossible assumptions. In practice, a generation ship to Andromeda is impossible. Not because of physics. Physics doesn't strictly forbid it. But because of practical, engineering, biological, and sociological limitations that may be even more fundamental than the laws of physics. A ship that can function for millions or billions of years without external maintenance is beyond anything we know how to build. An enclosed ecosystem that can sustain itself for millions of years without external input, recycling everything perfectly, with zero losses, is beyond anything nature has achieved or we've been able to engineer. A culture that can maintain itself, its knowledge, its purpose, and its technological capability over millions of years without drift, decay, or collapse is beyond anything human civilization has demonstrated. Human civilization is about 10,000 years old. A generation ship to Andromeda would need to maintain itself for 250,000 times longer than all of human civilization has existed. It's not just improbable. It's effectively impossible. There's also the fundamental question of motivation. Why would anyone undertake such a journey? You personally would never see the destination. Your children wouldn't. Your children's children wouldn't. Thousands or millions of generations would pass before anyone reached Andromeda. What's the purpose? To explore a galaxy we can already observe quite well with telescopes. To establish a colony that would have no connection to Earth whatsoever, no shared culture, no shared goals, that might not even remember Earth exists. To satisfy scientific curiosity about a place that will eventually merge with our own galaxy anyway. It's hard to imagine any civilization, no matter how advanced, committing the resources to such a project when the payoff is millions of years in the future and the benefits are unclear, especially when there are probably better uses for those resources closer to home. And there's one final problem that makes the entire endeavor pointless, even if you could somehow solve all the other problems. By the time any spacecraft traveling at realistic speeds could reach Andromeda, the merger will have already happened. Remember, the galaxies are approaching each other at 70 miles per second. In 4 billion years, they'll collide. If you launched a spacecraft toward Andromeda today, traveling at 1% of light speed, it would take 250 million years to arrive. In those 250 million years, Andromeda will have moved roughly 500,000 light-years closer to the Milky Way. You'd have to aim not at where Andromeda is now, but at where it will be 250 million years from now, when you arrive. And by the time you arrived, the galaxy would be well into the collision process. Its spiral structure would be disrupted. It would be developing tidal tails. Stars would be scattered. The neat, organized galaxy you set out to explore would be transforming into something completely different. If you waited longer to launch, hoping to develop better technology to make the journey faster, the problem only gets worse. By the time we develop technology to reach even 10% of light speed, which might take centuries or millennia of research and engineering, Andromeda will be even closer, and the window of opportunity will be narrower. Eventually, within the next few billion years, it will be too late. The galaxies will have merged. There will be no separate Andromeda to visit. There will only be Milkdromeda, and you'll already be part of it. The reality is inescapable. Andromeda is unreachable. Not because we lack imagination, not because we haven't tried hard enough, not because we need to wait for better technology, but because the universe itself imposes a boundary. The speed of light is that boundary. It's not arbitrary. It's not something we can overcome with clever engineering. It's woven into the fabric of space-time itself. Distances measured in millions of light-years are beyond that boundary in any practical sense. We can observe Andromeda. We can study it. We can photograph it, analyze its spectrum, measure its mass, count its stars, watch it approach. We can understand it better than any galaxy outside our own. We can predict exactly what will happen when it arrives. But we can never go there. Never walk on a planet orbiting one of its trillion stars. Never see its supermassive black hole up close. Never explore its star-forming regions or witness its supernovas firsthand. It's forever beyond our reach. This boundary that physics imposes applies not just to Andromeda, but to most of the universe. The observable universe contains about 2 trillion galaxies. The vast majority are far more distant than Andromeda, billions of light-years away. Even if we could travel at light speed, which we can't, reaching most galaxies would take billions of years, and the universe is expanding, carrying distant galaxies away from us faster than we could ever chase them. Galaxies more than about 4 billion light-years away are receding faster than light due to the expansion of space itself. Not moving through space faster than light, which is forbidden, but being carried by expanding space, which is allowed. We could never reach these galaxies, no matter how fast we traveled. The expansion of space itself makes them unreachable. We're confined to a cosmological horizon, a sphere beyond which we can never travel, no matter how long we wait or how advanced our technology becomes. We're stuck in our little corner of space, able to see vast distances but unable to traverse them. It's like being in a vast museum where you can see the exhibits but can't touch them or get close to them. You can observe, study, appreciate, but never truly interact. And yet, this doesn't make the universe less interesting. If anything, it makes it more profound. We can see things we can never reach. We can observe events that happened billions of years ago. We can watch galaxies collide, stars explode, black holes merge, all from the safety of Earth, looking out across distances that forever separate us from the rest of the cosmos. We can understand what we see. We can measure distances, calculate masses, predict futures. We can piece together the story of the universe using light that has traveled for millions or billions of years to reach us. That's extraordinary. We're a species that evolved on one small planet, orbiting one ordinary star, in one galaxy among trillions. And yet, we've figured out how the universe works. We've discovered the laws of physics that govern everything from atoms to galaxies. We've mapped the cosmos, traced its history back to the Big Bang, predicted its future evolution. We've understood that galaxies collide and merge, that black holes emit gravitational waves, that space-time itself is curved by mass. We've predicted the future merger of Andromeda and the Milky Way with precision, all using our brains, our mathematics, our telescopes, our detectors. We've transcended our physical limitations through understanding. The Milky Way and Andromeda are approaching each other. In 4 billion years, they'll collide. Over several billion more years, they'll merge into Milkdromeda. This merger is inevitable. It's already begun, in slow motion, playing out over billions of years. The galaxy's gravity is already affecting each other. Tidal forces are already at work, stretching and distorting the galaxies. The future is set. We can't stop it. We can't avoid it. We can't escape to Andromeda before it happens. We're bound to the Milky Way, confined by the speed of light, limited by the laws of physics. This is the boundary that physics imposes. not a barrier in space, but a barrier in possibility. Some things are possible exploring our solar system, sending probes to planets, perhaps reaching nearby stars someday with enormous effort. But some things are impossible, traveling faster than light, reaching other galaxies, escaping the merger. These limits aren't technological. They're fundamental. They're built into the structure of the universe itself, as unchangeable as the laws of mathematics. And yet, understanding these limits is itself a kind of triumph. 2,000 years ago, humans thought the stars were lights, attached to a crystal sphere rotating around Earth. 500 years ago, we thought the Milky Way was the entire universe, everything that existed. 100 years ago, we didn't know other galaxies existed beyond our own. 50 years ago, we weren't certain whether galaxies really collided or just passed by each other without interacting. Today, we know. We know that galaxies collide and merge. We know that Andromeda is approaching at 245,000 miles per hour. We know exactly what will happen when it arrives, and roughly when. We know why we can't reach it, and we understand the fundamental physics that makes it unreachable. We know the limits of what's possible. That knowledge, that understanding, is worth something. It tells us who we are and where we are in the cosmos. It tells us what we can do and what we can't. It tells us we're small, but we're not insignificant. Because we can understand. We can look up at that faint smudge of light in the autumn sky, that barely visible patch containing 1 trillion stars located 2.5 million light-years away, and we can comprehend what it is, how far away it is, what it's doing, and exactly what will happen when it arrives. We can understand the physics that governs its motion and the fundamental limits that keep us from ever reaching it. That's extraordinary. 4 billion years is a long time. Longer than Earth has been a planet. Longer than life has existed anywhere we know of. Longer than anything on our world has endured. By the time Andromeda arrives, the Sun will be in its red giant phase, having swollen to enormous size. Earth will have been uninhabitable for hundreds of millions of years. Humanity, if it still exists in any form, will be unrecognizably different from what we are today. We might have spread to other star systems, becoming a multi-stellar species. We might have evolved into something new, adapted to different environments, changed beyond recognition. We might have gone extinct, just one more species that rose and fell in the long history of life in the universe. We have no idea which path lies ahead, but the merger will proceed regardless. It will happen according to the laws of physics, indifferent to whether anyone is watching, following the same pattern that countless other galaxy mergers have followed throughout cosmic history. Andromeda will approach. The tidal forces will grow stronger year by year, century by century. The galaxies will pass through each other in their first close encounter. Stars will be scattered into new orbits. Gas clouds will collide, triggering waves of star formation. New stars will ignite, burn, and explode as supernovas. The galaxies will separate, slow, and fall back together. They'll pass through each other again, and eventually they'll merge into one. Milkdromeda will exist where the Milky Way and Andromeda once were. A single elliptical galaxy, larger and more massive than either of its parents, home to 1.4 trillion stars. And somewhere in that vast collection of stars, maybe there's still a planet. Maybe something still looks up at the night sky, wondering what happened, piecing together the history of the merger from the evidence scattered across space and time. Maybe they'll understand, as we understand now, that they're witnessing the aftermath of a collision that played out over billions of years. Or maybe there's nothing. Maybe the universe continues its expansion, with no one to observe it, no conscious minds to comprehend its beauty and its violence. We can't know. Thanks for staying with me through this journey across cosmic space and time. The collision of Andromeda and the Milky Way is one of the most spectacular events our region of space will ever witness. And even though we'll never see it happen, even though we can never reach Andromeda to explore it before it merges with our home, understanding it matters. It tells us something fundamental about the universe we inhabit. That everything is moving, everything is changing, everything has a history and a future. That there are boundaries we cannot cross, limits imposed not by our technology, but by the structure of reality itself. And that despite these limits, despite being confined to one small planet orbiting one star in one galaxy, we can still comprehend the cosmos. We can still understand what's happening 2.5 million light-years away. We can still predict the future and trace the past. We're small, but we're not insignificant. Because we can understand. And understanding is its own kind of reaching across the void. If this exploration meant something to you, a like or subscribe would mean a lot. Until next time, keep looking up.